I have nothing to do with peak bagging or with red giants. I still do frequency analysis, but if you think that red giants and premium sequence stars do not have anything in common, then you share my opinion until a couple of months ago. And why there are some things in common, although very different objects, you will see at the end of my talk. But under the light of recent developments, I will take the liberty to slightly shift the focus of my talk and slightly give it a different title, because last Thursday evening, my paper, Echography of Young Stars Reveals Their Evolution, was published in Science, and I thought it's a good start to introduce you all to the results described in there. And it has still something to do with NGC 2264, so it's only a slight shift of the topic. We have seen this diagram several times in the last, today and yesterday. It's well known to all astroseismologists, and we have described it. It's a Hertzsprung-Russell diagram showing all the different types of pulsators in there. And here you have the color code that shows you the G-mode pulsators are marked in red and the P-mode pulsators are marked in blue. But when you work with young stars like I do, you always look at this diagram and you think something is really missing. Because I would like to add a third dimension. I always wanted to do that. Because what you have here is a mixture of different evolutionary stages in one diagram. And of course it makes sense, but it's also a mixture of ages. And in most of the cases, it's not a big problem. But when you work with premium sequence stars, it is, and I'll show you why. You clearly can identify the really old ones, I call them now here evolved post-premium sequence stars, white dwarfs, and the pulsators. Then you go back in time, so the next early stage, let's call them the classical post-premium sequence stars, like the red giants, the Cepheids. And then you come to the classical main sequence pulsators. I just marked here the region of the beta Cepheids. And now it gets complicated because now we enter a region where you can have premium sequence, post-premium sequence, and main sequence stars showing similar pulsational properties, but are still different stars. So this is because they are in different evolutionary stages, and one goal of astroseismology is to probe the interior of stars, and the interiors change with evolution. So I think this is a very important factor. So if you look at this diagram in the Hertzsprung-Russell diagram, this region, why is this ambiguity of evolutionary stages? It's because the evolutionary tracks of pre- and post-main sequence stars intersect, as is shown in this diagram here. You see the solid lines show post-main sequence tracks and the dashed lines pre-main sequence tracks between 1.5 and 4 solar masses, just as a snapshot of a region. And you see they intersect, and I just inserted here an artificial kind of star with the typical values you get from spectroscopy. The arrow bars in temperature are 150 Kelvin, and log G is 0.2. Yes, you can do better, but you can also do way worse. So there is no way to distinguish the mass, there is no way to distinguish the evolutionary stage. So of course, here comes astroseismology into the play. It was already shown in 2001 in a paper by Suran et al. That if you observe a dense enough frequency spectrum, you can distinguish the evolutionary stages just from the pulsational properties. So you might have seen this diagram already before. You have now the pre-main sequence models are drawn in black, and the post-main sequence in solid lines, and the dashed lines are the post-main sequence excited frequencies. So the top row shows you model frequencies for L equals 0, so purely radial modes. There is not a clear distinction between the evolutionary stages. But if you go to L equals 1 or L equals 2 modes, you see already that the pattern is different. So that was a theoretical concept. And of course, it was up to us observers to try to test this hypothesis. And the first test we did was with ground-based data of a star in a young cluster where I found 9 pulsation frequencies. And we used the models by David Gunther. And he just assumed we don't know anything about this star. We just put the 9 frequencies into his model grid and find a solution. And you see on the left side, there is every point is the fit to a model. And you see that there is one clear minimum chi-square of close to 0 for the pre-main sequence models. But if you go to post-main sequence, it's about chi-square of 5 is the minimum chi-square you can get. So that was the first evidence that it would maybe be possible. But to go to the next step, we had to do a lot of additional observational work. And we need a couple of ingredients to continue in this work. So first, as an observer, you have to start by selecting your sample. Your sample, in my case, pre-main sequence stars. I just told you it's not easy to tell a pre-main sequence star from a post-main sequence star. So you have to deduce it indirectly from other parameters. So you use features that are typical for the pre-main sequence stage, such as if a star is associated to a star-forming region, or if it shows infrared ultraviolet excess, if it has emission lines, or is classified as Herwig-A star. But be careful. There are recent studies published from a colleague of ours in Belgium. Here you have two Hertzsprung-Russell diagrams. On the left-hand side, you have post-AGB and RGB stars, and on the right-hand side, young stellar objects. So it's even worse than what I showed you before, because they do not only lie in the same region of the Hertzsprung-Russell diagram. Post-AGB stars can have emission lines. They can have infrared excesses. So there is a lot of confusion, and you have to be really careful. But you can alleviate your problem by going to members of young clusters, and here we come to NGC 2264 as a very illustrative example. If you go to a cluster that is younger than 10 million years, you will have a massive main sequence consisting of the massive O and B stars, and everything that is from late B and cooler in spectral type, if you are sure that they are members of a cluster, they must be in the pre-main sequence phase. There is no way they can be evolved. So you have selected your sample. Next step is you need time series to discover the pulsation. And if you discover it, then you want to spend more time on it and analyze the variability. So the first light curves is the star that I just mentioned before. First light curves were obtained from ground, and then MOST came, and then CoRoT came. And we saw light curves like shown here. These are 5-day subsets in two observational seasons, on the left for V5 at 8 mon, and here for V5 at 9 mon, both members of NGC 2264. And you see it's a beautiful pulsating light curve, and you think, oh, wow, cool, and she even knows that's a pre-main sequence star. But it can be way more complicated, because when we saw this light curve obtained by MOST in 2006, was the first observational time, we were kind of surprised and shocked and happy and, all different mixed feelings, because you have, typical for a Herwig-A star, which has a circumstellar disk, you have irregular variability of up to a magnitude. And then we went back in 2007, and then we thought, wow, maybe this dip here, this repeats. No, it really does not repeat. The pattern is completely different. And on top of this irregular variability, you have millimagnitude pulsations. And the third panel, so the lowest panel here, shows you a zoom into this more quiet region of the data in 2007. So it can be quite challenging to disentangle the different types of variabilities. Okay, now you have your light curve. You have to now get the position in the Hertzsprung-Russell diagram. So you need fundamental parameters. It's not easy for young stars, which are generally faint objects. And so after a while, I succeeded to get high resolution, high signal-to-noise spectroscopy from different observatories like McDonald Observatory and ESO-VLT, ESO-HARPS, CFHT, and our 1.2-meter Mercator telescope. I added some low-resolution spectra from CTIO 1.5-meter telescope. And for a few of the stars, literature and archival data were available. So in the end, I could analyze those data and get effective temperatures, log G values, V sin I values, radial velocities, and metallicities for my stars. So next step done. So you can now put them all together in a Hertzsprung-Russell diagram and add the pre-main sequence evolutionary tracks, because you had made sure in the beginning that you're dealing with pre-main sequence stars. So this is the first time that you can really plot pre-main sequence delta Scuti stars. 34 is the size of the sample at the moment. And what you see here is temperature log G plane. You see the evolutionary tracks that are color-coded. Pre-main sequence stars gain their energy from gravitational contraction. So as long as these, mostly, let's put it that way. So as long as the tracks are given in black, gravitational energy is the main energy source, and the lighter the evolutionary tracks become, the less efficient gravitational energy becomes. And so when the tracks are given in yellow, That means the first non-equilibrium burning start, they stop then again because you see it's getting red again. And then, of course, when hydrogen burning starts in the core, then gravitational energy, gravitational contraction stops. And then you have these 34 stars. They lie between 1.5 and 3 solar masses. And the color code of the symbols is the percentage of critical velocity. It is important to make sure how fast your stars rotate, and it was generally assumed for a long time young stars rotate rapidly, but 50% of critical velocity is not too bad. The V sin I values lie between 10 and about 190 kilometers per second. So it could be worse, and we actually confirm the findings of Evelyne Alessian, who published a paper last year about young stars and their rotational speeds. And then, of course, we have to add now the astroseismic information to the whole story. So we do the same plot again, but now you see the symbols are now color-coded with the highest observed P-mode frequency. You know from theoretical astroseismology the value of the acoustic cutoff frequency. And in observations, you have to have a measure of this somehow. So the closest observational value that would represent the acoustic cutoff frequency is something like the highest observed P-mode frequency. And so if you color code the sample now with this highest P-mode frequency, which is given here in microhertz, the color scale is on top, you see that there seems to be a trend that the least evolved stars that are farthest away from the suns seem to be slower pulsators than the ones close to the suns. It becomes even more clear and more evident if you pick a sample of stars that is born from the same molecular cloud, so from NGC 2264. So you have 9 stars, 9 Freeman sequence delta Scuti stars of the cluster, and you can see from A to I, they are labeled here, you will see in a moment why, that the slowest stars are furthest away and the bluest star is close to the 0-H main sequence, which was a very exciting result. And it's even more exciting if you then compare it directly with the amplitude spectra. So you have here a stack of 9 amplitude spectra compared to the plot you just saw before in small. So from top to bottom, or from right to left in the Hertzsprung-Russell diagram, you see the amplitude spectra plotted. In gray, it's the original amplitude spectrum. The black lines are the observed pulsation frequencies, and the right line is the maximum, the highest observed P-mode frequency. And sometimes it's it has a tiny amplitude, and so the inserts show you that it's of statistical significance. So this means that the slowest pulsator is the least evolved Freeman sequence star, and the fastest pulsator is the most evolved Freeman sequence star. This means that we could use the oscillations of Freeman sequence stars to trace stellar evolution, which is very exciting and what I was always looking for. So I promised you at the beginning, I tell you what Freeman sequence stars and red giants have in common. Maybe you remember the paper by Joris de Ridder in 2009, 5 years ago in Nature, a stack of 9 amplitude spectra where you could see how the power shifted with evolution. And here, coincidentally, it's again 9 Freeman sequence delta Scuti stars where you can do the same thing. So there is something in parallel here. The other thing that they have in common is they started with MOST and CoRoT data. Both topics started with MOST and CoRoT data because we should not forget MOST also in the role in red giants. Then, of course, the red giants had the giant leap using the Kepler data, which is still missing for Freeman sequence stars because they were never part of the original Kepler mission. So how do we go on from here? What is the future prospect? I would really like to use MOST as long as it is possible. So I hope the MOST science team will continue to grant time if possible. And I'm hoping for K2 because Kepler has looked in a high galactic altitude. There were no Freeman sequence stars. K2 would have the possibility. We also wrote a white paper on another cluster, NGC 2244. In field 0, I was very excited. The original center coordinates would have allowed that in one CCD we have several stars of NGC 2264, but unfortunately the final decision was to move away from this region, and I lost it again. So I don't have 4 years of Kepler data, and I'm still waiting for a Kepler data point. And so I never give up. So there was field 2, the announcement, and I added, I wrote the proposal, and the star that I just showed you before is included in that. So I still have high hopes. I think it's important also for the exoplanet community because, as we mentioned already several times today, star and planet formation are connected. So whatever we learn about young stars and about their ages, their evolution, might also influence the evolution of planets. And I finish now with my final conclusion. Coming back to the introductory talk by Ron Gilliland, the Space Photometry Revolution for young stars has already started with MOST and CoRoT, and please also see Anne-Marie Cody's talk on Thursday. She's talking about the completely different types of young stars, but similarly exciting. I really hope for K2, and we have definitely to include those stars in Plato because there is a high potential. Thank you very much.
I think Johan was the first.
Thank you. These are very beautiful results. It's fantastic to see such a large sample of pre-main-sync stars. And it's so nice to see that little suitcase doing something useful. So,
yes.
But I'm a bit worried about your interpretation in terms of the frequency of maximum power, because you're quite right. For solar-like stars, there seems to be a clear relation between the frequency of maximum power and the acoustic cutoff frequency. We don't understand why, but it's very nice diagnostics. Here we're talking about modes that are excited through the heat engine mechanism, where we don't really understand the distribution of amplitudes. There must be a relation between the amplitudes and the structure of the star, and if nothing else, there's a relation between the characteristic frequency and the mean density, which would give more or less the same kind of behavior as you are seeing in your analysis. So I think you have to be a little bit more focused on the frequency and maximum power and a bit more, look a bit broader at the properties of the oscillations for this kind of diagnostics.
Yes, I fully agree. I only want to clarify one thing. The frequency of maximum power would mean I take the frequency, if I put it in other words, with the highest amplitude. What I did here is to use the highest observed frequency in frequency value, which is slightly different. I can assure you that the same relation is visible if you use the frequency of maximum power, but it's maybe not as beautiful, so I picked this one. And the other thing is, if you compare it to red giants have been observed by CoRoT, by Kepler, so you have large samples of stars. I have a mixture of MOST, I have a mix of CoRoT, of ground-based photometry, and sometimes Series spectroscopy. I have to take what I get. So give me a homogeneous sample, and then we go and tackle this question. But I fully agree. There's a lot of work to do, and so, yes, fully your opinion.
Were there any other questions? Yep, a quick one down the back.
It's more a comment. Presumably you can add tests to your list of missions where you can potentially
yes,
do
correct.
stuff.
Yes, I will.
Thanks. Okay, so let's thank the speaker again.